Okay, this is our official review of capacitors. Maybe not our official review, we did that in class today. So, we're going to begin by talking in broad terms about capacitors from Gauss's law. And then here's the basic way to go through that. So we're going to call it Getting C by Gauss. So, first step, find the electric field. So with the first step, you are using Gauss's law to find the electric field. And so, the electric field for sphere, E is equal to Q enclosed over 4 pi epsilon naught r squared. For a cylinder, E is equal to lambda over 2 pi epsilon naught r. And for parallel plates, E is equal to sigma over epsilon naught. Now you'll notice that each of these has that epsilon naught thing underneath of them. That can always change. A dielectric will go from epsilon naught to the dielectric constant times epsilon naught. So a dielectric will reduce the overall electric field. So after you've found the electric field, you're going to do step 2, which is find the voltage, which is the negative integral of the electric field in our region with respect to R. And we're going to go from the outside, usually B, to the inside, A. Or in the case of parallel plate capacitor, from one side to the other. So across the distance D. And we've done this a few times, but what we get for each of those, voltage for a sphere is Q over 4 pi epsilon naught 1 over A minus 1 over B. For a cylinder, the voltage is lambda over 2 pi epsilon naught times the natural log of B over A. And the voltage for the parallel plate capacitor is sigma over epsilon naught times D. And then our third step in all of that, after we've done all that, third step is to take and say, alright, the capacitance is total charge over that voltage we just found. And I am skipping a lot of steps, but this is a review. So the capacitance for our sphere is 4 pi epsilon naught over 1 over A minus 1 over B. The capacitance for our cylinder is 2 pi epsilon naught L over the natural log of B over A. And the capacitance for parallel plate capacitor is A epsilon naught over D. Now the thing that these all have in common is that the total capacitance only depends on the dimensions, not on how much charge or how much voltage you have. And if we continue our discussion of dielectrics, the dielectric decreases it decreases E and V and increases the overall capacitance. That's what a dielectric does. So there are some things that we like to do as far as questions for dielectrics go. And for this, we will talk about a capacitor attached to a battery, and then an isolated capacitor. If we charge up a capacitor attached to a battery, and then we take a slab of dielectric material, dielectric constant kappa, and slide it in here, the voltage remains constant. Because we're hooked up to a battery, so that's not going to change. But the voltage remains constant. The capacitance is going to go up, and because of that, the total charge on our object, if the capacitance goes up, the total charge that object can hold is going to increase as well. That's what inserting a dielectric into an attached capacitor does. When the thing is isolated and we do the same thing, if it's already charged, we cannot change the charge because of conservation of charge. We are stuck with the same Q that we had, which means which means this time, because the capacitance goes up, the voltage is going to have to go down. These are two different situations for adding a dielectric to a capacitor. And then if you look at all of this work through here, as you add a dielectric to each one of those, you are decreasing the voltage. You can see how it's going to change everything. And you're decreasing the electric field. Another thing that we like to do with dielectrics is pour them into a sphere or a cylinder. And so if we look at this, and say we have a dielectric in half of it and then just nothing in the rest, it's going to change a few things. So up here at the top, I have a specific electric field. It's going to be whatever Q on that half is, we'll call it Q1 divided by 4 pi epsilon naught r squared. Down here, we're going to have a different electric field. That electric field is going to be Q2 over 4 pi times kappa times epsilon naught times r squared. Because of the presence of the dielectric, we have reduced the electric field by that much. Now, looking at it, the total voltage here has to be the same, and there's a rule because of that. Voltage on a conductor surface is constant. There's not going to be any change to that. Now, because the voltage on this conductor surface is constant, we're stuck with a different Q on each little bit. So the part with the dielectric is going to hold more Q than the part without the dielectric. That's what inserting this has done. If we want the voltage, we're going to take the integral of this one with respect to R to give me voltage in that region, and the integral of this one with respect to R to give me voltage in the other region. And in order for the voltage to remain constant, we're going to have different Q's, and they're going to be different by the ratio of their dielectric constants. At the same time, we could take and construct another situation where we take our same, and this could be a sphere if you wanted to get fancy, it could also be a cylinder. We take the same thing and then we put inside of it sort of a layer of dielectric. In this case, electric field is going to be weird. First off, we can see that there's only one way to have charge all the way through this. I can get if we have plus Q on the inside, even throughout all of this, we're going to have negative Q on the outside. Since we have that dielectric all the way around, we're going to have the same Q all the way around, but it's going to make the electric field weird. So if we call the first radius A, and the next radius B, and this middle one all the way to here. Oh, sorry. So A, B, and then let's call that little one C. That doesn't make any sense at all. Ignore that. We're going to call this A, call that B, we're going to call that C. So we have different regions for the electric field. From A to C, the electric field is equal to Q over 4 pi kappa times epsilon naught times r squared. And then from that's A to B. And then from B to C, my electric field is going to be Q over just 4 pi epsilon naught r squared. In a cylinder, that would be 2 pi and then r and not r squared. But we have different regions of the electric field. And when we did the voltage for this, our voltage would be the integral from C to A of the electric field with respect to R. And what we're going to see is that the total voltage is a combination of voltage 1 and voltage 2. Because the nature of this integral says we're going to have to add them all up. That's what adding a dielectric would look like to things in cylindrical capacitors and spherical capacitors. So what that gives us is a couple of things to look at. First off, we're going to go ahead and call this something. Hopefully we're going to call it the right thing. That is a set of capacitors in parallel. Okay, when capacitors are in parallel, the voltage is going to be equal all the way across. Now, we also saw that the total charge was different. Total charge is going to add. And if we take and substitute our little formula for capacitance for Q, where we see that Q is equal to C times V, since all the voltages are the same, when capacitors are in parallel, total capacitance is going to be capacitance 1 plus capacitance 2 plus capacitance 3. Now, over here, we have something fundamentally different going on. Over here, we have a capacitor in series. I have to go through one capacitor and then the other. And in series, the charge has to be the same. Q total is Q1, is Q2, is Q3. But from this, and really looking at that little integral, we see that the total voltage adds. And then applying sort of the same logic, but in this case it looks just a tiny bit different, saying that voltage is equal to Q over C, and since all the Q's are the same, we have 1 over total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that's sort of our setup for series and parallel capacitors. Now, let's look at doing just a simple calculation for inserting an extra dielectric into there. So, let's start off with parallel. And let's do it for a plate. So top plate, bottom plate. We'll say this has an area A. Imagine it extending back. And a separation between the plates of D. And what we're going to do is take a dielectric and stick it in half. So we have some dielectric in half of this capacitor, dielectric constant kappa. And what we see here is that we have capacitance 1, capacitance 2, say K1 and kappa 2, just to be fun. So, capacitance 1, parallel plate capacitors, it's A epsilon naught over D, but we have half of A, so A over 2 times epsilon naught over D. But because of that dielectric, we have an extra kappa 1 in there. Same thing for capacitance 2. Capacitance 2 is A times kappa 2 times epsilon naught over 2D, because we have half of the area. So our total capacitance here, since this is parallel, I have a choice. And what I mean by that is I could either go from the top plate to the bottom plate through the dielectric, or I could go from the top plate to the bottom plate through the other dielectric. So what we see for the total capacitance in this case is A times kappa 1 times epsilon naught over 2D plus A times kappa 2 times epsilon naught over 2D. But they're going to add together in this case, and you're going to see the overall capacitance change that way. The next thing that we could do is take the same idea of our parallel plate capacitor with A and separation D, and then sandwich in some of our dielectric like this. To where we have K1 at the top, K2 on the bottom. In this case, we still have capacitance 1 and capacitance 2, capacitance 1 being at the top. Well, in this case, it's still A epsilon naught over D, but we're splitting in half D, so it's A times kappa 1 times epsilon naught over D over 2. And then for capacitance 2, same idea, A times kappa 2 times epsilon naught over D over 2 again. But since we're in series this time, we have to go through the region containing the first dielectric, and we have to go through the region containing the second dielectric. When we get the total capacitance, it's 1 over the total capacitance equals D over 2A dielectric constant 1 times epsilon naught. Nope, ran out of room. Plus D over 2A times dielectric constant 2 times epsilon naught. And then you could add those together and find a common denominator, simplify, and then flip the whole thing over. But that's what you would do with a parallel plate that way. The parallel plate, it's easier to see that the charge has to be the same on the top and the bottom. So, we don't use this too terribly much, but we do, and we are going to start putting capacitors in circuits. So if we have capacitors in series like this, and what we get from a circuit, the battery is going to pump positive charges onto this side of my capacitor, which is going to induce a negative charge over here, which means, it's polarized, so we have positive on top, positive on one side, negative on the other. So we have the same amount of charge going all the way across. which agrees with what we were saying about capacitors in series. Capacitors in parallel, though, for a capacitor in parallel, you have one capacitor here, you have another capacitor here. So when the battery is pushing out charges to begin with, the battery pushes out some charge to this capacitor and even more charge to the next capacitor. That's why we see the charges adding when we're in parallel. And the voltage is staying the same. If it's attached to this end of the battery, the voltage is the same. So, when we look at combinations of capacitors and doing a whole lot of things together all at once, and I don't want to go through the time of doing this. We did do an example like it in class, I think. But if we have a battery and we're attached to this capacitor, and we have another capacitor, you know what, we will do this example, and another capacitor. Let's see. Let's say we have 2 microfarads here, 4 microfarads here, and then 3 microfarads, and let's get a little fancy and say that we have an 8-volt battery. So what we want to do, and we'll write down some goals over here, find Q and V for each capacitor. And this is the same method that we're going to use when we start talking about resistors. So the first thing we want to do is simplify that parallel branch. So we got 8 volts for our battery. Coming through here, we have our 3 microfarad capacitor that we're not going to touch. We're not going to do anything to. And then we're going to put those two together as one capacitor. Now, since those guys are both in parallel, we just add them together, and we've got 6 microfarads, which is great. So then we're going to take and we're going to combine the rest of it. So we got an 8-volt battery, and we're just going to say that we have 1 capacitor on there. To get the total capacitance here, we have to add reciprocally. So 1 over C total is 1 over 6 plus 1 over 3, which is 1/6 plus 2/6. So 1 over C total is 3/6, and that makes the total capacitance 2 microfarads. So 8 volts, 2 microfarads. And now that we have that, we can say that the voltage is, oh, we already have the voltage, sorry. 8 volts is dropped across there, so we can say that the total charge, Q total in this case, is going to be CV, or 8 volts times 2 microfarads, giving us a total charge of 16 microcoulombs. So 16 microcoulombs goes there. Now, since this is just a combination of two things that are in series, we can say that they share the same charge, 16 microcoulombs, and up here 16 microcoulombs. And for each of these we're going to calculate the voltage. And if we remember, voltage is equal to Q over C. So this side is going to be 16 over 3 volts. And this side is going to be 16 over 6 volts, or 8/3 and 16/3. So that's going to leave us, I'm sorry, I'll go ahead and give you numbers on that. 2.66 volts and 5.33 volts. When you add them together, you still get 8. So, because this 6 microfarad capacitor is just a combination of two things in parallel, and we know that in parallel the voltage is the same, each one of these has 2.66 volts across it. And if we wanted the charge, we're just going to take and multiply 2.66 times 2. To get 5.32 microcoulombs, and then 2.66 times 4 to get 10.64 microcoulombs, and we figured the whole thing out. So what that takes is going down and reducing it to one capacitor, and then going back up and expanding it out and looking at every combination that we made to figure out what it was. I hope that we are a little bit more familiar with resistors, but for combinations, for resistors, the big thing that we're using the big thing that we're going to use is Ohm's law, where V equals IR. That's going to tell me the voltage across a resistor that has current I running through it. So we are in series for a resistor. The current is constant all the way through. We only have one choice, so current is current, total 1, 2. And in series, just like we saw with capacitors, the voltages add. Voltage total is voltage 1 plus voltage 2. And with resistance total, you have R1 plus R2. They add. And then in a parallel combination, you have constant voltage, so V total is equal to V1 is equal to V2. Your current adds, so I total is I1 plus I2. And then you have resistance that goes together in a slightly weird way. 1 over R total is 1 over R1 plus 1 over R2. So that's a series circuit and a parallel circuit. Now when we do combinations, usually we can do what you just saw with the capacitor, but every now and then you have to deal with Kirchhoff's laws, and we're just going to call them K-laws. And with Kirchhoff's rules, you have one, the loop rule, where all of your voltages where all of your voltages must add to 0. This is, of course, the conservation of energy. And then you have the node rule, which is what we saw in the parallel thing. And in the node rule, current splits. So current in must equal current out for the node rule. And we're not going to run through a whole example, but we are going to draw one out and talk about what you would do with it. So, to get a little bit familiar, like with what we did in class today, and one of the questions on your UT homework, let's say we have a 10-volt battery coming out of that into a 2 ohm resistor. And that's going to come down through a 3 ohm resistor. And then on the other side of that we have maybe a 4-volt battery and another 2 ohm resistor. And what we want to know is the current through all of these, or the power of one of the resistors. So we're going to guess current run 1 runs this way, current 2, because it's with the second battery, runs that way, and current 3 goes in that direction. Now, what we do with Kirchhoff is choose loops. And so the first loop that I'm going to choose is this one. I go in the direction of my arrow. So for my first loop I have 0 equals 10 volts minus 2 times I1 minus 3 times I3. And then my second loop, just for simplicity's sake, you can do what you want, would be through there. So I have 0 equals 4 volts minus 2I2 minus 3I3. Right now I have two equations with 3 unknowns, and that's no good. So I just did 2 loop rules, loop rule, loop rule. And I'm going to do a node rule. And so what that means is, this is my node. If we did a close-up of our node, here's our node. We have I1 coming in, I2 coming in, and so we have to have I3 come out. And so what I'd say for that is that I3 is equal to I1 plus I2. Now the rest of solving this is just, and I say just jokingly, solving a systems of equations. It can be difficult. My strategy on this would be plug in for I3 for each of these. Then you have 2 equations, 2 unknowns. Substitute or solve for I1 in one of them, plug it in for I1 in the other one, find I2, and go back and forth. This takes a while, so in my opinion it's really important to know how to set up a couple of equations from these rules and to really understand the loop rule, because that's what we're going to use next when we talk about RC circuits. So for an RC circuit, we have resistors and capacitors together in a circuit. So let's look at charging first. So in a charging circuit you have a battery and a resistor, a switch, and a capacitor. And so we're going to, at time equals 0, flip the switch. We'll give these things values of V, R, and capacitance. Let this be very general. So when time equals 0, we're going to flip the switch. And so the voltage across the capacitor when time equals 0 is 0. And it wants to get filled up. So we will have some current. We'll let red be time equals 0. If we have voltage of the battery here, we're going to have voltage of the battery on this side of the resistor. Then we get 0 here, 0 here, and the capacitor, if it's initially uncharged, we get 0 there all the way across. So we see that the voltage across the battery is equal to the voltage, sorry, not voltage across the battery, the voltage across the resistor is equal to the initial voltage that we have on the battery. And if that's the case, we know that the current in this circuit is going to be the voltage on the battery divided by the resistance. And we know that the charge on the capacitor to begin with is 0. All this is at time equals 0. Now, as time goes on, we'll do this in a different color, as time goes on, the capacitor, time goes on means a long time afterwards or infinity, the capacitor is charged up and it's equal to the charge on the battery, which means we can't push any more charge onto it anymore, so the current is 0. And if we have a 0 current, that means the voltage across the resistor has got to be 0. And then the charge on my capacitor is the capacitance times the voltage of the circuit. So in this case of charging, here's my initial condition and my final condition. And then if we want some time in between, we're going to do a Kirchhoff loop rule. So 0 is equal to the voltage of the battery minus IR minus the voltage of the capacitor, which is going to be voltage of the capacitor, Q over C. And we're going to use the relationship, because we're charging, I is equal to the increase in my charge over time. We're going to take that relationship, plug it in, and say 0 is equal to V minus dq over dt times R minus Q over C. And what that's going to give us eventually, and again, it's a review, so you can look up the rest of it, is Q as a function of time is equal to my total charge, capacitance times the voltage, times 1 minus e to the negative t over RC. RC is that time constant. Sometimes they call that tau. Now, if we want the current as a function of time, we're going to need the derivative of this. So we take the derivative of this and we have the voltage over the resistance equals e to the negative t over RC. Now, since there are two different voltages that we can speak of, we have the voltage of the capacitor and we have the voltage of the resistor as a function of time. The voltage of the capacitor is a function of Q. The voltage of the capacitor is Q over C. So if I wanted to get the voltage of the capacitor, we would take the charge as a function of time and plug it in there, over C. Voltage of the resistor, that's Ohm's law, that's I times R. So we would take our current as a function of time, multiply it by the resistance to give us that. Okay, this is what a charging circuit looks like. With discharging, we're starting off a little bit differently. In a discharging circuit, what we have is a charged capacitor with some initial value for voltage. We're going to attach it to a resistor. And when time equals 0, we're going to throw the switch and we're going to let the charge flow. Now, because it's charged up, it has the ability to push charges through the resistor. So because it's charged up, so initially the voltage on the capacitor is some initial V0. So the charge on the capacitor, Q, is equal to C times V0. And initially, current is going to flow. So initially the current is going to be V0 over R. Now, as time goes on and this thing runs out, time is equal to infinity, the voltage on the capacitor is going to be 0. The charge on the capacitor is going to be 0. And the current in the circuit is going to be 0. We don't have any more push. So, as a function of time, we're going to do another loop rule. So 0 equals the voltage on the capacitor, which is Q over C, minus IR. Now, in this case, things are a little bit different. Since we're discharging, I is equal to the opposite of the change in charge, or the change in time. So, we have 0 equals Q over C plus dq over dt times R. And I'll go through this. We have dq over dt times R equals negative Q over C. So dq over Q is equal to negative dt over R times C. And what we're going to want to do is take the integral of both sides of this equation. We're going to go from 0 to t, but since at 0 I started off charged, we're going to go from Q0 to some later Q. It's an integral we've taken before, so the natural log of Q over Q0 is equal to negative t over RC. Exponentiate both sides, even if that's not the right word. we're going to use it because I think it's cool. And then Q as a function of time is Q0 times e to the negative t over RC. And you can take the derivative of that again to get the current as a function of time. And then do the same thing to get the voltage across the voltage across the resistor and the voltage across the capacitor. Now, sometimes, since you have a test tomorrow, assume that it's more likely than not you have a capacitor circuit that is tricky. And by tricky, I mean it's not going to be directly connected to the battery. It's going to be in parallel. So when you're looking at something like this and you're looking at how the whole thing is going to behave, it's good to remember what it means to have that thing uncharged. So when time is equal to 0, the voltage across the capacitor is 0. The charge on that thing is 0. And it acts like a wire. So your circuit in this case would look like the battery attached to a resistor attached to another resistor. Oh, sorry. But it's attached to a wire. Now what that means for current in this instant is that your charge is going to go through the first resistor. It's going to get here. This branch has more resistance, so it's going to bypass it all together. And so that circuit in red is what's actually going to happen. So the initial current here would be the EMF of the battery over just the resistance of one resistor. Now, as time goes on, so an infinite time later, the voltage on the capacitor is equal to, well, we'll talk about what it's equal to. The voltage on the capacitor, it's full now, so there's no more current going through the capacitor. And it's going to act like a break in the wire. So in that case, you have your battery, resistor, resistor. And since this capacitor is full, it can't push any more charge through it. So that's the only place that charge is going to flow in this circuit, and the current afterwards is going to be EMF over, in this case, we'll just say R plus R. You're going to have numbers, you have to figure it out. But it acts like a brake. Now, we're tempted to say that afterwards the capacitance is equal to the EMF in the battery. Well, that's not true. Because of this first resistor, we have the EMF of the battery, then we have the EMF of the battery minus IR1. EMF of the battery minus IR1. We have lost some voltage here. So the voltage across the capacitor here is actually going to be equal to the voltage across that second resistor. So it's good to remember that voltage of the capacitor will be equal to the element it is in parallel with. That's what's going to determine the voltage of the capacitor. Okay, one more quick thing. I know we're approaching about 45 minutes. Look at graphs. So when we're charging a capacitor, Q as a function of time is going to look like this. We're approaching that final value of Q, and that's what a Q equals CE times 1 to the 1 minus e to the negative t over RC graph looks like. And then for current as a function of time, it's going to die. And that's what an I is equal to I0 times e to the negative t over RC graph looks like. Now discharging is similar but not quite the same. When we discharge our capacitor, Q is a function of time, when we discharge our capacitor starts full and then dies out. And that's, when we solve for it, Q is equal to Q0 times e to the negative t over RC. And for a discharging capacitor, we start off with some current and we lose it. And you'll notice when you take the derivative of that, you're going to end up with the same thing. I is equal to I0 times e to the negative t over RC. Okay, so I think that about covers a lot of what we did in this unit. Good luck on your test tomorrow. I feel like you guys are really ready for it. So, again, good luck. See you tomorrow.